A lot of times you're going to be given a rational function like this and be asked to do a two-sided limit, like in part D, where we want to do the limit as x approaches negative 2 of x minus 5 over the absolute value of x plus 2. Now again, the first step I do is I plug negative 2 in. I get negative 7 over 0. The fact that I have a number over 0 and I'm doing a two-sided limit means that I have three choices at this point. It's either going to be infinity, it's going to be negative infinity, or it's not going to exist. I got to figure out which one of those it is. So the only way for me to properly explore that is I do have to do the left-hand and right-hand limits. So A, B, and C, I've done all the preliminary legwork in parts A and B. Here, I got to do kind of the same thing I did in parts A and B, just to do part D here in and of itself. So I got to find out what the limit of this rational expression is as x approaches negative 2. And when I do that, I realize that negative 2 from the right-hand side, which means values like negative 1 or even positive values, I'm going to get a positive value in the denominator, and I'm going to absolute value that. So I do have a negative 7 being divided by a positive answer. That's going to be negative, which means that the limit as x approaches negative 2 from the right is going to be negative infinity. When I approach negative 2 from the left, again, I'm going to be picking a value that's less than negative 2. And when I do that, and any number less than negative 2, when I add 2 to it, it's going to give me a negative. But when I absolute value a negative, it becomes positive. So I'm still going to have a negative 7 over a positive answer, which means it's still going to be negative. So the left-hand limit's also going to be negative infinity. And since the left-hand limit and the right-hand limit agree with each other, I know that the limit as x approaches negative 2 from both sides of x minus 5 over the absolute value of x plus 2 equals negative infinity. Anytime that when you evaluate a limit and you get a 0 in the denominator and a number other than 0 in the numerator, that tells me that I have the existence of a vertical asymptote. We talked about those too when we were talking the same thing we were talking about holes. Okay? Because remember, having a 0 in the denominator in each one of these cases does signify a domain restriction. And a domain restriction could either be a hole, which we would call a removable discontinuity, and that's because of the cancellation type thing. Or we also had a vertical asymptote, which is sometimes referred to in calculus as an infinite discontinuity because it's a discontinuity. You're going to have to break up the graph to account for that vertical asymptote, which does involve infinity. The other thing that's going to happen is sometimes, like if I'm looking at A, B, and C, when this graph approaches negative 4, here's negative 4 for instance. If I approach from the right-hand side, the graph's doing something along the lines of this. When I approach from the left-hand side, the graph's going to be doing something along the lines of this. Whereas I look at part D, if I approach negative 2, both from the left and right, it's going to do something along the lines of this. Each one still indicates I have a vertical asymptote going on there. I have basically something that graph's going to avoid. It's just the direction in which they avoid them. So that's why, again, in calculus they often refer to a vertical asymptote as an infinite discontinuity.